We're finally getting to the day where we start figuring out why we've spent so much time on series over the semester. And today it might not all become clear to you, but hopefully over the next couple of weeks, it will become clear why series are useful. What we're going to do today is we're going to learn something called Taylor series. This is going to be a way to represent functions as power series. So we remember power series have x2 powers in them. And so our goal is to take something like the function sine of x or cosine of x and rewrite those as power series. And you might think that that seems like a weird thing to do. Why am I going to rewrite sine as an infinite sum of things? And the reason is because power series, the individual pieces are just polynomial pieces. So we have like x to the fifth or x to the sixth. Those types of things are much easier to work with than something like sine or cosine or even e to the x. So if I can turn sine into something that has polynomial pieces, then that will be nice. Even though it's an infinite polynomial, it is still nicer than sine is. And we'll learn how we can make these not infinite, where we can just take part of the series and use that to approximate things like sine or cosine. Your calculator is actually doing this when it calculates values for sine or cosine, which is kind of fun. So for now, we might not understand exactly why we're doing this, but we'll get around to that eventually. And the way that we write functions as power series is what is written below. This is using Taylor series. So this looks kind of funky, but once we start doing examples, it will get better. So if a function has a power series expansion at a point A, then it's going to have this form below. Once again, this looks weird. So let's just look at this form. So this form, the nth term is the nth derivative at the value of a divided by n factorial times x minus a to the n. And we start at 0. So my first term is just the function at that point. Then we take the derivative and plug in the point, divide by 1 factorial, we have x minus a. And we just keep doing this. So if we're going to try and get this power series representation, we're going to need to start with some derivatives. This expression here is called the Taylor series of our function centered at a. If our a value is equal to 0, we call that special case the Maclaurin series. So a Maclaurin series is just the same thing as a Taylor series centered at 0. So don't think of a Maclaurin series as anything different. It's just a Taylor series where we're plugging in 0 for our a values. But we'll use both of these terms just because I want you to be familiar with both of them. So let's jump into how do we do this. So this problem is asking us to find the Taylor series for f of x equals 1 over x squared centered at -1. So in this case, our a value is -1. Okay, we know that all the Taylor series are going to have this form here. So let's write this form down and replace the x's with the a's with -1. So I'm going to use this notation over here instead of the summation notation. So we're going to have f of -1 plus f prime of -1 over 1 factorial, x minus -1, so that's going to be x plus 1, plus f prime double prime of -1 over 2 factorial, x plus 1 squared, and let me do the third term as well, the third derivative at -1, 3 factorial, x plus 1 cubed, and we're going to keep going with this. Okay, so all I did was replace the a's in this equation up here with -1s. Okay, we need to do some more work. So our function is 1 over x squared. So what we're going to do now in these problems is we're going to start finding derivatives. I've written up through the third derivative here. We might need to find more derivatives to start trying to find a pattern, but let's start with this. So the function I'm working with is 1 over x squared, which I'm going to rewrite as x to the -2. If I take that derivative, I get -2 x to the -3. The derivative of that is positive 6 x to the -4th, and the third derivative will be -24 x to the -5. Okay, so now I need to plug -1, into each of these. So f of -1 is 1 over -1 squared is going to be positive 1. F prime of -1. -1 to the third is negative. So the negatives are going to make this positive 2. double check, make sure you agree with me. -1 to a positive power is going to give me +1 for this piece. So I'm going to get 6 out. And again, the third derivative is going to become positive because I'm going to have -1 to the 5th, which will be positive, or will be negative. So remember, the reason that I'm saying this is to the 5th is this is -24 over x to the 5th. When I plug -1 into this, I'm going to get -24 over -1 to the 5th, which is -1. So I'm going to have -24 over -1 gives me +24. Okay. So now that I've gotten these values, I'm going to go back and plug them into my expression that I have up here. So let me do that in a different color. So f of 1, that's just 1. F prime of -1, that's 2 over 1 factorial, x plus 1. This piece was 6 over 2 factorial, x plus 1 squared. So it's 24 over 3 factorial, x plus 1 cubed. Okay, we're going to want to try and find the general term. So let's simplify these expressions. And you might be able to find this general term without simplifying, but let me simplify. So this is going to give me 1 plus 2 times x plus 1. 2 factorial is just 2, so 6 over 2 is 3. So I'm going to have 3x plus 1 squared. 3 factorial is 6. 24 divided by 6 is 4. I'm going to have 4 times x plus 3 x plus 1, x plus 1 cubed, and so forth and so on. Sometimes you might need to do a couple more derivatives and write a few more terms just to see if you can figure out the pattern, but I think we can find the pattern here without doing that. So let's see if we can find the pattern. So it looks to me like we have an x plus 1 to an n in here. We usually kind of forget about that first term. That first term is going to be what happens when n is 0. So if we forget about that first term for a minute, usually that will make life a little bit better. So let's see if we can find a pattern for the rest of the terms, and then we'll hope it works for that one. Okay, so this is my first, that's my second. So it looks like this number out front is 1 more than what the exponent was. So my number out front needs to be n plus 1. Okay, that's going to work for all those terms except for the first term. Let's check and make sure it works when n is 0. So if n is equal to 0, we're going to have 0 plus 1 is 1. X plus 1 to the 0th is 1. So we're getting 1 out. So that works for the first term, and it should work for other terms as well. So that is our general series. So what this series is this series is a representation for 1 over x squared. We're going to have to figure out like a radius or interval of convergence to figure out exactly what x values these are equal for. We'll worry about that in class. But what this is doing is allowing us to represent 1 over x squared as a polynomial. 1 over x squared itself is not too terrible to work with. It's a pretty easy function to plug numbers into. But like I said, if we're going to rewrite like sine of x or cosine of x as a polynomial, that will make life easier for us. Okay, so we'll get lots of practice over the next 2 days with these.